Alrighty. Okay. Well, new day, new streak. Last hard one, although I feel like I'm somewhat close in it. It definitely did stun me, so unless I go back to it, it's gonna be streak 1, hopefully today. Longest balanced substring part 1. You're given a string S containing lowercase letters. A substring of S is called balanced if all distinct characters in the substring appears the same number of times. All distinct letters appear the same number of times. Okay. The length of the longest, return the length of the longest. Okay. So here it's 4. A, B, B appears both twice, or A and B appears twice both. Here it's 4. Z, A, B, C all appear once. And here it's 2. A, B appears once. Okay. Seems understandable enough. Question is what to do. Guessing this is sliding window. Good old sliding window. Is it actually? Oh my god, the balancing continues. You extend out the window. Ah, mother. A, B, C. A, B. That's good. B, A. Hmm. Z, Z, A, B, C, C. So it feels like if I do a sliding window here, it needs to be kind of backwards looking because I don't know how you would, because in theory if there's like this is the start of the string and there's more characters afterwards, in theory there's a long enough string that like all these things, all the letters shown so far reappear and up their frequencies up to the same frequency. So if I do a backwards looking one, so from any given index, what is the longest substring where that index is the ending index? What is the longest substring that you can make where all the letters appear at least the same time? So in theory, if all the letters are the same, then you can just use that same letter with that one frequency, with that frequency that the letter has. And then once you see a different letter, you have to go back to the highest frequency. God. I feel like if I can solve this, I should be able to solve the hard one yesterday. It's 1,000, so in theory this could be just a n squared thing. Oh no. Oh no. This is the same as the last one where part 1 was a small length and then part 2 was a longer length that was hard, so yeah, I'm pretty sure I can do an n squared approach here. I'm also pretty sure an n squared approach is not going to be fast enough for the hard version. Okay, let me think. Fresh day, fresh thinking. A, B, B, A, C. Any given index, Well, for sure, for sure. Hmm, what is for sure? C A B. If it's B here, then this means the frequency is now 2. So I go backwards based on the frequency of the highest so far. So if it's C, there's 1 frequency, so I should go back 1. Now, no, it's not quite right. Because if it's something like P, 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 I go back P, now there's P, P, P. So you go back increasing by the highest frequency, except if it's the same letter. the number of letters times. No, you go back. If it's AC, you just go back 1. But here, if it's BAC, then you need to go back 2 more. Because in theory, it could be like a C and A before that. So it's like you go back a certain number of indices, then what's the point of that? That's just a quick check to see if those, like if you go BA, if the front here is like, there's some letters here and then it's like this, then if it's BBAC, then in theory there could be these 3 letters all appearing 2 times, so you go back 2 more. But then it could just be that there's other stuff that, like 2 Ds or something. Doesn't really prevent you anything. Although maybe it does skip over certain indices because you know that if BBAC is back 4, then there's no point in checking like a 5th or 6th because you need to go all the way to 8 to have anything that's actually balanced. Not that, no, sorry, anything up to 6 for anything that's balanced. So let's say there's a D here, so you go BBAC, this recognizes that there needs to be 6 at least, like 2 B's, 2 A's, 2 C's. So when you do 6, now there's a D, so now you recognize there needs to be another C and another D, so you go back 2 more here. This is very inefficient. Like, what the hell is this? It's not, no way that works. The substring is balanced if all characters in the substring appears the same number of times. Yeah, this goes back to the previous one where I wasn't sure how to find like the frequency of a particular subarray in O of 1-ish time. Somehow store that information. Or if not store it directly, then store something that can compute that information in O of 1 time. Frequency and maybe the set of values in any subarray given the starting and ending index. Do 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 do. Daba daba daba. Hmm. Can I iterate an index forward, keeping track of some sort of stack of information, whereupon that stack of information has a computable difference? Has a computable difference. A, B, A, B, B, A, C. 1A, 1A, 1B, 1A, 2B, 2A, 2B, 2A, 2B, 1C. So the frequencies by index, for each new letter, it's either going to bump up the frequency by one of a given letter already appearing, or add a new letter that obviously is going to appear once. I mean, I could do the difference between two frequencies, the difference between the distribution of letters between two indices is the subtraction, right? Like between the last index and the third index, there's one additional A, no additional B, one additional C. So 1A, 1C is the distribution of letters in that subarray. And if you subtract it by 3, then it's 1A, 1B, 1C. Which is technically balanced. Last letter is a C. The last letter before that is an A and a B. C-A-B. The letter before that's a B. I wonder if I can do like a binary search here. Binary search, where I'm guessing. What am I guessing? I'm guessing the frequency of the longest, the highest frequency in that substring. Binary search, guessing this frequency. Because if I did guess the frequency, then it's just going to be, I guess the frequency, then the frequency times the number of different letters is the length. So I'm guessing both. Guessing the frequency. No, I'm guessing the length, right? Because if I just guess the frequency, if the frequency is like a high frequency, high frequency could lead to a shorter balanced substring if there's only like one different character of that frequency versus like a slightly lower frequency but two characters, like 5 C's versus 4 A's, 4 B's in the balanced substring. So I have to guess the length of the balanced substring. And in binary search, guessing the length of the balanced substring means that I have to do an O of n operation. No, it's not going to work. Balance, because in binary search, if I guess a certain value and that value is true, then technically it means that everything that is less than that value is also true. That's not. There has to be like two distinct ranges of true false return given the parameter. But if it's like true for, say, oh, it's true for a balanced substring of length 10, it doesn't necessarily mean it's true for a balanced substring of length 9. Like 10 could be true, 9 could be false, and 8 could be true or something like that. So not binary search technique. Well, I don't think it's the binary search technique. I guess I'm not gonna guess the number of distinct letters in this in the longest balanced substring. That doesn't make sense either. How do you track this? Track these frequencies between indices without having to do a straight subtraction between the frequency arrays. I mean, I guess you could do subtraction between the frequency arrays, it's just not going to be. It's kind of like an O of 26 operation. O of 26 operation. Then you still have to iterate over every possible subarray length or every possible subarray, which is going to be O n squared. O of n squared, huh? A, B, C. It's easy as 0, 1, 2. You think about the letters in your set. You iterate over your end indices. Somehow you need to do some sort of constant operation from a given n index. Constant operation from a given n index to every prior. Every prior. One, two, three. Hey. Huh. 1A, 2Bs, 1A, 1C. Does that help at all just to chunk it? I have 1C, 1A, 1B here implied. Now you have 2Bs. So you need another A, 2A, 2B. We'll see how this helps. I mean, I guess it helps in the case where you have something like A, B, 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 2A, 3B. So you can immediately say that 3B is something. And then what? And then 2A. Can't even do the 2A's. Guess it was something like 3A, B, B, 3A, 2B. Then you could do 2B and then another 2A. A, B, C. A, B, C. Company. Appear exactly one time. Maybe I can do the trivial case. The set of values, the set of distinct, the length of the set of distinct letters, and then if each frequency matches that, if there's the same frequency for every letter, then perfect. Return the length of the string. Man, I swear, the frequency stuff has killed me before. Maybe I just need to go back to looking at some answers. Because I swear I've gotten stumped on frequencies before. What haven't I gotten stumped on? Jesus. Stumped on arrays, stumped on graphs, stumped on dynamic programming, stumped on everything. Frequency. Like, you can't do a prefix array on frequencies, I don't think. I guess prefix arrays are similar to frequency differences. Frequency arrays have sums of values in your array. Take the difference between those sums to get the sum of the items between them. This is like another dimension to the frequency arrays. One extra dimension? 26 extra dimensions? Huh. Open the window. Open the window. A. Let's think backwards. So if I'm at a certain index, so say there's a bunch of letters and then A, B, B, A, C comes out. So it could be 1C, 1A, 1C, 1A, 1B, 1C, 1A, 2B, 1C, 2A, 2B, 1C. Going backwards from C, there's 1C, 1A, 1C, 1A, 1B, 1C, which is balanced. 1A, 2B, 1C, 2A, 2B, 1C. So somehow this is balanced, or it's balanced. And let's say there was like a C right here, right? 2A, 2B, 2C. And that's balanced. Somehow I would need to the window always has the current letter. Current letter is the starting point. Okay, let's compare this versus the last index being A. This A, so it'd be like 1A, 1A, 1B, 1A, 2B, 2A, 2B, 2A, 2B, 1C. So all these things, the frequency of them are the same. They're kind of like these, but with 1C appended to them, or 1C incremented to them. So that's like n squared. For each index, iterate over the frequency tables at every previous index. Add the new letter to that frequency table, and then see if that is balanced. It's pretty bad. It's so bad. Okay. I'm just gonna code it. God damn. So what's the deal here? So um, I'll have a frequency table. Maybe I'll just have I'll just have a default dictionary for to store each frequency at each index. And is the length of the string. This is obviously not going to work with hard. Frequencies or distribution, I guess. I'll just do frequencies at index is going to be a default dictionary. Returning an integer for everything in range of n. So keep frequency at every index. And then I'll say answer 0 for every index in range n. I'll take the letter at the index, and then I'll update the frequency of everything before that. Say the prior in range of, I guess starting with index, all the way to the first, index 0. Increase the frequency of this letter at each index. By 1. And then I'll check if balance from prior to index. So for every, I'll say the min frequency is infinity. The min frequency needs to be high. And the max frequency is 0 for every prior letter in the default dictionary, which is frequency at index, no prior. If is there a better way of doing this? Maybe I should make the frequencies not default dictionary but an array of 26. Array of 26. Then I could use min and max and whatever. I guess use the values. I wonder if that's just slower. Values equals. Actually, yeah, I'll just do values equals frequency. At index prior. And then the min frequency is just the min values. Max frequency is max values. If min frequency equals max frequency, then it's balanced. So answer equals max of answer equals max of answer, and I'll just say min frequency times the number of letters, so it'd be something like the length of values. Guess that's it. Going on here, 6 versus 4. 6 versus 4. Really? Print the values. One frequency of the letter. Guess I really don't need this because they're just initialized. So it does z first, so that means it's 1. And then it does this thing. It's 1 here, it's 2 here. So why is this one value 1? Frequencies at the letter. Okay, let me go ahead and print the index here. So index should be 0, 1, 1, 1, 0. That seems fine. Thought this would be 2. Because there should be 2 z's at that point, no? 2 z's. Rather than, so the value being the frequency of z at index 0 should be 2 at that point. Oh, I'm an idiot. I'm a dum-dum. Alright. Ah. Yeah. It's probably better if I did an array. rather than default dictionary. Though if I had an array, what would the initialization of the array be? Zeros? Zero is the frequency. And then the max frequency would be what? How would I... Max frequency I can find using max of the array, but then the min frequency would have zeros in it, which is kind of a pain. I wonder if this is slowing it down, taking the values iterator. Could manually do it, I guess. Count equals 0 for every value, for every p value and frequencies at index for this prior. Count plus equals 1. I guess I don't need to know the key. Back to min frequency starting with n, max frequency starting with 0. I'm doing something like if min frequency is, or if the value is lower than the min frequency is equal to the value. If the value is bigger than the max frequency equals value. And here's just time to count. Answer equals max of answer and count times min frequency. I think that should do the same thing. Not enough values to unpack. Oh, I see. Yeah. How to iterate over? I guess it's enumerate. Enumerate. How to iterate over dictionary entries. Items. Okay. Maybe it's slower, maybe it's faster. Okay, it's slower. God damn. Alright, okay, so let's go back. How would I do it without default dictionary if I have an array of 26 frequencies? Oh, I see. I could figure out what exact letters there are, map each letter to an index, and then it would be, no, the zeros would still be there. Zeros would still be there. So I have to manually do it still. To find the max using it, but the minimum would still have zeros in it. Yeah, I don't think this is worth it. Let's try to optimize this using an array where the default dictionary is just still too slow. Still too slow, still too slow. So what I'm going to do is I'm going to go ahead and call this a wrap. Not my best. Like, I think there was something slightly faster than this kind of. The last time I did this a couple days ago was something slightly more optimized, but we landed here. Could do something similar here, but I need to just think about finding the non-n squared approach. So I'm going to call this one. So, unfortunately, this uses the same inefficient n squared approach to handling subarray frequencies. Basically, actually, probably worse than how I did the problem 2 days ago that had a similar concept. But at least this is much simpler and easier to code. So basic idea is for every ending index, find add that letter to the frequency to the frequencies, or I guess distribution of letters from all prior indices up to that index. At each index. Actually, I could probably do. What I probably should do is I should probably do it forward looking, so that it can break early. Yeah. Each prior index after adding the letter. Check. I guess I can't do that, can I? Because I still need to add the index. Still need to add the letter. The string is balanced between prior and current index. Return longest. If it is, update the answer with that length. Return the longest length. Alright, I do need to iterate over all prior indices to update the index. That's fine. And then what I can do here is only if the length of the difference between these two indices is longer than the current answer. So if the let's see, if the length between them, so the length between them should be index minus prior plus 1. Prior starts at index. I think it's plus 1 is greater than answer. 0, get the values. If the min frequency, then I already know that this is going to be better, so I need to do maximum. So I don't need count anymore. Count was the previous thing. Okay. Should be slightly better. Should be slightly better. Oh, okay. Time complexity. This is gonna be O of n squared. As it uses a nested for loop to iterate over each ending index, where to uses a nested for loop where outer loop iterates over the ending indices, and the inner for loop iterates over all prior indices, updating frequency tables and checking for bounce. Technically, checking for balance is kind of an O of 26 operation. It's 26 letters, so it's not quite, I don't consider it quite like a constant speed operation, but it's not quite O of n operation, obviously. Space complexity is going to be O of, you keep the distribution at each spot in the, at each index, so I guess it's like O of 26 times n, or yeah, or O of n, I guess, since for every index this tracks the frequencies of letter to that index.